in the last lecture, we had described what is called a lattice and what is its defining feature. So, lattice's defining feature is its translation symmetry. Now, we want to come to crystal and how it is different from crystal. So, let me write this in the form of an equation. Crystal equals lattice plus the third entity that I had mentioned in the last lecture, motif. So, crystal will have atoms, and where are the atoms going to come from? The atoms are going to come from the motif. So, let us take some examples to understand this. And this addition of lattice plus motif is actually an addition of vectors, as we will see a little later. So, let us first take a one dimensional example. Consider a lattice which is simply a row of points in one dimension, stretching again from minus infinity to plus infinity. Now, what I do? I take a motif which consists of one atom. So, it consists of one atom, and I place this atom at the center of the atom should coincide with the lattice point. That is one way I can place this atom. So, I can place this atom at every lattice point. So, now I have a crystal structure, a one dimensional crystal structure, where an atom is present at every lattice point. But then a motif can be more complex than this. It can consist of two atoms, and let us say this motif consists of two atoms like this. So, now I have a two atom motif, and just the way the atoms are there in the motif, that is the way the atoms will be present at every lattice point. So, as you can see here that one atom whose center coincides with the lattice point and the second atom is somewhat shifted. Now, motif need not be the same atom itself. Let us consider a second motif which is something like this. So, now I have a motif of two different atoms, one is a green colored atom, the other is a red colored atom. So, let us take this example as well. And this time I decide not to coincide any of the atom center with the lattice point. So, I can, for example, let me first put the green atom. So, now as you can see, the atom center is not coinciding with the lattice point, and the second, the red atom goes out here. So, neither of the atoms center coincides with the lattice point, it is absolutely fine. So, whether the center of the atom coincides with the lattice point or it does not matter, the arrangement of the atoms in the crystal is identical. So, therefore, we are actually free to choose the origin, but we will see later that there are some preferred choices for the origin in a crystal, but we will consider that at a much later time in the course. Now, the same idea I can go to two dimensions now. And let us take a motif of the type say I have one kind of atom and another kind of atom in this orientation. So, as you can see, this motif has a somewhat different orientation, and the same orientation must be maintained in the lattice. and I can then put this, for example, one can put first, let me put first the green atoms. And then I put the red atoms. As you can see that we are maintaining the same orientation. So, this becomes a two-dimensional crystal. Now, let us look at this crystals a bit more deeply. So, the lattice, for example, the first lattice, the one-dimensional crystal and its lattice, let us say its translation vector was A. Then you will notice that the individual atoms in the motif follow exactly the same translation. So, for example, the atom center which coincides with the lattice point would have the same translation that the lattice has, which is and similarly the second atom will also have the same translation. So, what we notice is that the individual atoms in the motif will follow exactly the same translation as dictated by the lattice. And the same is true for the second pattern also, that I have a one-dimensional crystal where the green atoms will have the, suppose the lattice translation is A, then the green atoms will have translation of A and the red atoms will have translation of A. So, one thing to note is that the two atoms, for example, even though in the first case all the atoms are the same, but there are pair of atoms which are not translationally equivalent. What does that mean? What I mean is that this is not a translation vector. So, this is important and this should be noted. In the second case, if I look at, so if I have a translation of A and B, so the green atoms follow the translation of A and so on, and the green atoms also follow translation of B. Similarly, the red atoms would have a translation of A and translation of B. So, again I am emphasizing that the individual atoms in the motif will have the same translation. Now, this again, whether it is one dimensional or two dimensional, they are all infinite arrangement of atoms. So, therefore, we need to reduce it down in order to describe this structure. I need to look at a method of describing it by describing a small unit which we call as the unit cell. Let us just consider the two dimensional case, and let us define the unit cell with respect to a lattice. So, here is a two dimensional lattice. In order to describe it, I will describe it by defining a small unit. So, one such unit that I can describe is a parallelogram. It looks more like a square or a rectangle here, but it could be any arbitrary parallelogram. So, this is one such example. Now, what does it do? So, let us say my translation vectors are A and B. So, if I translate now the entire unit cell by A, then you will see that the two dimensional lattice will get replicated. If I translate it by the vector B, then again, so that way by translation through A and B, I can replicate the entire lattice. Now, is this the only possible unit cell I can have? No, I can have other unit cells as well. For example, I can have a unit cell like this, in which case my translation vectors could be different. So, here for example, it is A, and here it would be, let me call it as B prime. In fact, I can draw even more skewed unit cells, which are all perfectly valid unit cell. For example, I can have a unit cell in this manner. Again, this is A, and this translation along this direction is B double prime. So, I have these different unit cells that are coming up, but when you translate it by the translations A or B prime or A and B double prime in the three different cases, I will end up generating the same lattice. Now, one can also think of a unit cell which is something like this. So, in this case, this is a larger unit cell than any of the other unit cells, and it has more number of lattice points as well, but this again, so here the translation vectors would become 2A and B. Again, this unit cell when translated through 2A and B would generate the identical lattice. So, let us look at first of all the smaller unit cells, the three smaller unit cells that I have drawn. In each case, all the three unit cells, which is cell 1, then I have cell 2 and cell 3. All the three unit cells, let us look at how many lattice points are there. So, in cells 1, 2 and 3, number of lattice points per unit cell. So, let us look at in all the three cases, the lattice points are at the corners of the unit cell. And if you think about it, for example, let me consider a lattice point out here. You could see very clearly if I draw another unit cell next to it, you will see that this particular lattice point is shared by 4 unit cells. That means, effectively only 1/4 of a lattice point is part of a single unit cell, and now there are 4 such lattice points would be there, here all the 4 corners, and 1/4 is part of the unit cell, which means effectively I have 4 into 1 upon 4, which is equal to 1 lattice point per unit cell. Now, the same is true for cell 2 and the same is true for cell 3. Now, consider cell number 4. Now, cell 4 if I look at, there are obviously again corner lattice points and there are two more lattice points in the center of these two opposite edges. From the corner, I will get effectively one lattice point. So, number of lattice points per unit cell would be equal to 1 from the corner. Now, look at the other two lattice points out here and out here. This is again, you will notice that I can draw one more unit cell next above this, and therefore, this particular lattice point in the center of the edge will be shared by two unit cells. So, effectively half a lattice point is there in the unit cell and there are two such lattice points, which means the contribution would be 1 from the edge center and 1 from the corners, effectively giving me 2 lattice points per unit cell. Now, another property that you would be able to see if you do a bit of very simple geometry, that the cells 1, 2 and 3, the cells 1, 2 and 3 all have same area, and it is very easy to prove. In the case of cell 4, this has obviously the area is more, in fact it is precisely twice the area. So, cell 4 has an area which is 2 times cell 1 or 2 or 3. Now, we give a special name to cells like 1, 2 and 3. We call all such cells which have only one lattice point per unit cell, we call them as primitive unit cell. And a cell like cell 4 is called a non-primitive unit cell. Now, if you want to look at it, how many primitive unit cells I can have? Well, actually in fact I can have infinite number of primitive unit cells, and non-primitive, again I can draw even bigger cells having more, including more lattice points, or I can have different shapes having the same number of lattice points. So, again infinite. So, therefore, any lattice can be described by one of the infinitely available unit cells to describe the lattice. So, one conclusion that I have here is I have infinite number, the choice of the unit cell. So, but therefore, we have a conventional choice of unit cells that we will slowly develop, that how these conventional choice of cells are taken. Now, we come to one more concept called the primitive translation vector. Well, a translation vectors A and B, again we are just looking at 2 dimensions, but the same thing will apply to 3 dimensions as well. A and B would be considered as primitive translation vectors if the unit cell area is smallest out of all the cells that are available to us, smallest, and that we have just now saw that cells 1, 2 and 3 are primitive unit cells and their area would be the smallest. So, which essentially means that the primitive, or we call vectors A and B as primitive translation vector if it defines a cell which has the smallest area. In 3D, we will have obviously 3 vectors A, B and C. So, if these were to be primitive, then it would be the smallest volume. So, obviously, if I have primitive translation vectors, then I would also have non-primitive translation vectors. So, which means that it will define a unit cell which has an area in 2 dimensions bigger than the primitive unit cell, which is the case for cell number 4 out here. Now, does that make a difference? Well, in a sense that if I now have to think about translation vector, lattice translation vector, which describes all the lattice points, lattice translation vector, say R, is defined as N1A plus N2B, where N1 and N2 are integers. Now, in the case of non-primitive, what happens? If I put a lattice translation vector as again N1A plus N2B, but then N1, N2 can take fractional values. This can be easily seen here. For example, if I can consider, let us say this is my origin here out here. So, if I have to define a lattice translation which will take me from the origin lattice point to, let us say, this lattice point designated as A, my total lattice parameter, this 2A, which I can call it as A prime. So, then this would have to be A prime by 2, which means it has to take a value of half the lattice parameter. So, now I will close this lecture here, and in the next lecture we are going to extend the same idea to 3 dimensions.